Section 5.3 dot product, length, and orthogonality. See this definition. U and V are two vectors in Rn. Then the dot product or the inner product of U and V is defined as in this equation. U dot V is the same as U transpose V. And first we multiply the corresponding entries, U1, V1, U2, V2, and the last one is U and Vn here, and we sum those numbers to get the dot product. That's the definition of dot product. In a metric vector multiplication AB, the product of row of A and the column vector V is dot product. So you already used the dot product. Now here we define the dot product. Okay, U and V are given. We want to find U dot V. We'll follow the definition. U dot V. We multiply the corresponding values 1 times 3 from second entries and minus 2 times 2. From third entries we have 2 times minus 4, and we sum those numbers. Then 3 minus 4 minus 8, so we have minus 9. That's the final answer. Quite simple, right? U, V, W are vectors in Rn, and C is a scalar. Then we have these rules. You can make dot product with opposite order, and you can see quite easily it must be true, because even though you put V in front of U, it doesn't matter. The product, the multiplication of the corresponding entries will not change the result. So that here, this is true. For these two terms, when W is common, then you can make here the dot product after adding U and V first and dot product. This rule can be used when you see this one. Then rather than making twice of dot product, you may combine them and compute this one and one dot product. In real computation, it will be more efficient. Now, for scalar multiplication, you can multiply a scalar C for U or V, or after dot product, just one multiplication of C. Either way, you can do this do the computation. So also, from the computation point of view, this one will be most efficient. And U dot U must be non-negative. Okay, here we multiply corresponding entries. So the first one from here, they are the same U1, so it will be squared. From second one, U2 squared. From the third ones, and eventually the last one, so that this addition must be non-negative, because each term is non-negative. Now, U dot U is 0, then that means all this U1 to Un must be 0, which means U is 0. So U dot U equals 0 is the same as U equals 0, right? Now we define the length or norm. sometimes it is called Euclidean norm. Length of V is non-negative scalar value, and using that notation defined by here. Now V norm is square root of V dot V. Now that is, here we have square root of V1 squared plus V2 squared, and last one will be Vn squared. By squaring both sides, we have V norm squared is same as V dot V. For any scalar value C, if you multiply C to a vector V and take the norm, then that is same as the norm of V times absolute value of C. You have to be careful. You have to put here absolute sign for the scalar. Okay, here W is a subspace of R2 spanned by a vector V, and 34. Pictorially, we can visualize W in this way. Here, that's in x direction is 3, and y direction is 4. So we have a vector from origin here, 34 position. That is a vector V. Span, so that W is now span of V. That is same as the collection of linear combination of the vector. That means C of V. For every scalar, we have the vectors and it's collected. The vectors are collected so that the W will make a straight line passing the origin and then including the vector. Okay. That is the subspace W. Find the unit vector U that is a basis for W. Quite easy to get unit vector U equal. Now V divided by length of V. The length of V is, okay, let's try to find the length of V. V there on equal same as square root of V1 squared, V2 squared, 30 squared plus 4 squared. That's 9 plus 16, so that this is 25, which means that is 5. Okay, so here we have that is 105, and then here that is 3 and 4. So that is the unit vector. So it'll be a smaller one around here. That is U, and scalar multiples of this U. So if we collect all of them, then eventually it becomes the subspace W. So U itself will form a subspace, a basis for W. Okay. Now we define distance. U and V are in Rn, and we define the distance between U and V in this way. Distance UV is same as norm of U minus V. So eventually this is same as the length of the vector U minus V. Okay, here we'll compute the distance between two vectors U and V. First we form U minus V. U is 7 and 1 and V is 3 and 2, so that the first component must be 4, second component must be minus 1. So U minus V norm is same as, by using the definition of the norm, here the first component squared, 4 squared, plus second component squared. So that is square root of 16 plus 1, which is 17. So the distance is square root of 17. The pictorially, we can explain that one. U is here, so you may draw another vector here from origin to U, and V is here. Now minus V is this one. So U minus V means that start from the origin, go to U and minus V. So we reach at that one. That is now, if we, so that this position is U minus V. So that is exactly this one. But if we consider this parallelogram, then length of this one is the same as length of that one. So that the distance between two vectors is really the distance between two vectors. So that distance is the distance between two vectors. Okay. Two vectors U and V in Rn are orthogonal if their dot product is 0. Here we have the Pythagorean theorem. Two vectors U and V are orthogonal if and only if U plus V norm squared is same as U norm squared plus V norm squared. Okay. Now let's draw a figure. That is U and that is V. Okay, that is U and that is V. Then here from the origin, that one will be now U plus V. You learned from high school the Pythagorean theorem. Once it is the triangle, that angle is right angle, then length squared plus length squared of this one is same as the length squared of this hypotenuse. So that is exactly this equation. It is true only if it has this angle 90 degree. So that means this 90 degree is orthogonal. So orthogonality is the same as right angle. So geometrically, orthogonal vectors make 90 degrees, right? Okay. The inner product can be defined as, in this equation, U dot V as U norm times V norm times cosine theta. Here, theta is the angle between U and V. Let's try to find the angle between U and V. We'll solve only part B, and you can do this one yourself. Okay, we have to compute U dot V, U norm, and V norm, and we can find cosine theta. And out of that value, you can decide theta. Okay, okay, start with U dot V. That is the corresponding entries, multiplication, that is a minus 1/2, and this multiplication is a 3/2, and sum, which makes 1. Now U norm here, and square root of 1 squared is 1, square root of 3 squared is 3, so that is square root of 4, which is 2. And V norm is same as square, that is 1/4, plus the second term square will be 3/4. So the addition must be 1, so that is 1. So we share this equation. U dot V is 1 equal, U norm is 2, V norm is 1. Now cosine theta. So we have cosine theta equal 1/2. Okay, so we can easily get theta pi over 3. Okay? That's the final answer. This is end of the section. Thank you.